Okay, this is going to be our sixth video in our Sources of Magnetic Field series. And in this video, we're going to be covering section 28.6. In this section, we're going to set up what's known as Ampere's Law. We're not going to do any examples of Ampere's Law. I'm going to devote the entirety of the next video to doing examples. So we're just going to do the setup. We're going to derive Ampere's Law. We're going to talk about where it applies and where it doesn't apply. And then in the next video, I'll do some examples. Or I'll exclusively probably do examples in the next video. Okay, so to sort of set the stage here, let's sort of think back to some of the work we did in the course already. So in chapter 21, we started off looking at electricity. We wanted to calculate electric fields, and the way that we did that was we said, okay, well, the electric field, the full macroscopic, or like all of the electric field at a certain point, is going to be equal to all the tiny little contributions of electric field from all the charges around that region, right? So we went through and we kind of did this integral over all the different infinitesimal charges, and then we got the sort of full electric field at some point. To get this dE, we kind of used the expression for a point charge, and then we kind of argued that you can break up any macroscopic object into a collection of point charges and just sum over all those point charges, right? And to get the charge of a single point charge, we used Coulomb's law, and this is the expression that we ended up using. So we kind of integrated over this as our integrand, right? So that was fine. In some cases, it was a little complicated, right? The integrals can get a little messy. In other cases, it wasn't too bad. But then in chapter 22, we saw that for some situations where we have really symmetric charge distributions, right, where we're dealing with like a charged sphere or something, where we can really see a lot of symmetry, where depending on how we rotate this thing, it kind of looks the same. So in a number of different ways, we have these nice symmetries that allow us to make simplifications, right? And so we saw that in those situations we can apply Gauss's law, which dealt with electric flux initially, but then we built it up into Gauss's sort of full law here. And we saw that just by looking at the charge enclosed in some sort of a closed surface, that we can get E in some of these cases if there's sufficient symmetry that we can pull E out of it, right? And in those cases, this was often less work, right? Because we just have to look at, well, what's the enclosed charge? Can we pull out the information about dA, like the full area of whatever we're integrating over? Can we get to E easily? If the problem is sufficiently symmetric, we can, and this is an easy way for us to get E, right? So this is great. Now in this chapter 28 here, what we've been doing so far is we've been calculating the magnetic field, right, in a very similar way to the way we calculated the electric field in chapter 21. We kind of say, okay, well, I want the full magnetic field at some point. To do that, I'm going to add up all the tiny little infinitesimal contributions to the magnetic field. Where do I get these infinitesimal contributions to the magnetic field? Well, we use the Biot-Savart law, very much like we used Coulomb's law in chapter 21. So now we're kind of using this as our integrand, and we're integrating over all these tiny little contributions to the magnetic field, right? And again, this works fine if we can do the integrals, but we run into situations where it's either very difficult to do the integrals, or we just can't do them analytically, or we can do them, but it's a lot of work, and it would be nice to have an easier way to sort of do this, right? So we know that we can't use Gauss's law for magnetic fields, right? Gauss's law for magnetic fields, we saw, just gives us this sort of magnetic flux through any closed surface is going to end up being zero, right? And because it's zero everywhere, we can't really extract. Well, it's zero for every closed surface. We can't really extract any useful information about B because this thing is just telling us nothing, basically, right? So this kind of leaves us with a question, right? The question is there some other procedure or some other equation that we can use to calculate magnetic fields more easily than using the Biot-Savart law, right? Something maybe like Gauss's law, but that's going to work for magnetic fields, right? So very similar to chapters 21 and 22, where in chapter 21 we used this sort of Coulomb's law and doing that integral, we saw in chapter 22 that there was a sort of easier way for highly symmetric situations using Gauss's law. Is there an equivalent situation for magnetic fields? And the answer is yes. Ampere's law is going to give us another way of calculating magnetic fields in situations where we have enough symmetry that we can actually get to B using this technique. Okay. And so Ampere's law is going to be phrased in terms of a line integral, which is going to be sort of just like an integral around a closed path, and we're going to be integrating around this closed path. We're going to be integrating B dot dl. So dl is going to be these tiny little segments of length around our path, and B is just a magnetic field at that point. So we need to dot the two of those together, and then solve this integral around a closed loop. Okay, so this isn't the full sort of Ampere's law, obviously. This is just a sort of setup. We need to phrase it in terms of this, and we're going to kind of derive Ampere's law by looking at how this integral looks around a long straight conductor while we follow a circular path around the conductor. Okay, so we're going to look at it in that one very sort of restricted case, but we're going to see that we can, in a few steps, generalize this so that it works for basically any current carrying conductor where the current is constant in time. Okay, and I'm going to talk about all that as we go along here. So I just realized that I might not have chopped off the bottom of the PDF here. So yeah, this is all stuff from before. So this is all old stuff that I'll chop off. Okay, but for now, where were we? We were here, right? Okay, so earlier we found that at some distance r from a long straight conductor, we have a magnetic field that has the magnitude shown here, right? So our magnetic field, the magnitude of our magnetic field around a long straight conductor is going to be equal to mu naught times the current running through the conductor over 2 pi r, where r is our distance from the conductor, right? And remember that the right-hand rule gives us the direction that B is going to be following, and all of our magnetic field lines are concentric circles around the conductor, right? So let me just quickly draw one. Let's say we have a conductor. We have current coming up out of the page. It's a long straight conductor, so we're kind of like looking down the pipe at it here. And if we use our right-hand rule, our magnetic field lines are going to be going around this thing like this, right? Okay. So these would be our magnetic field lines, and this is our current coming up towards us. Okay. Okay. So we're now wanting to do a line integral around a circle of radius, say r, right? So let's say we pick some radius r here. Let's say this is the radius r. We're going to want to do a line integral. Maybe I'll do this in a different color, where we're going to choose a path that goes around this thing in this direction, let's say. Okay, so we're going to do a line integral, adding up all these tiny little segments of dl as we go around. Okay, so this is the line integral that I talked about above here. We're going to do b dot dl, where the full line integral is going to go around the circle that we see here at radius r. Now, because B always points along the path being followed by the circle, and the circle that we're drawing is basically directly on that magnetic field line, we're always going to find that B and dl are parallel, right? And because B and dl are parallel everywhere, our B dot dl is just going to go to B dl, right? We don't have to worry about direction because they're always parallel, okay? And also, because r is constant, right, because we're always at a constant radial distance away from our conductor, well, the magnitude of B is also constant, right? It's not changing, so B can be pulled outside of the integral. So we end up with the integral around our closed loop of B dot dl. Well, this just becomes the integral around the closed loop of B dl, right? We don't have to worry about the dot product because of the parallel nature of B and dl. And we can pull B out of the integral because B is constant at that constant r, right? Well, in that case, we can just write what B is. So writing down B here gives us this part here is our value from B from above. And what is this value of an integral around a closed loop, adding up all these tiny little dLs which make up the circumference of a circle? If you add up all the tiny little pieces that make up the circumference of a circle, what do you get back? Well, you get back the circumference of the circle, right? And that's this. This is the closed loop integral dl around a circle of radius r. Okay, so we end up with both of those results. We can see that this is going to cancel with this, and we end up with just this remaining here. Okay, and so we see in this very sort of restricted case where we're looking at a conductor that's long and straight, where we know B, and we are looking at a contour that's a perfect circle that we're integrating around at a constant r from that conductor. We end up with this expression. We end up with the integral around the closed loop, this circular loop of B dot dl is equal to mu naught I. Okay, and so even though we've kind of built this for a very, very restrictive case here, we can see that it generalizes quite well. We're going to take a look at that here in these next few diagrams. Okay, so the first thing to notice is that the result is independent of radius. So we could have chosen a circle of any radius we wanted. We could have chosen this inner radius. I could choose a radius way out here. It really doesn't matter what we choose. In the end, we're going to get the same result. Okay. Now let's take a look at what if instead we chose a path not following the direction, like these path integrals are directed, right? So we chose this direction to do the path integral, and it just happened that it lined up with our current. Well, with the direction of the magnetic field that is dictated by the direction of the current, I should say. What if we chose the opposite direction, right? If we chose the opposite direction, and instead of doing our integral around the loop in this direction, where we can see that our magnetic field is going to point in that direction just by using the right-hand rule on the current here, what if we chose the other direction? Well, we're going to pick up an overall minus sign, right? So here we see that our closed loop integral around our circle of B dot dl is equal to mu naught I. Here it's going to be equal to minus mu naught I, because at every point, every little contribution adds up negatively instead of adding up positively, right? And so this already sort of suggests that we can kind of end up with a right-hand rule from this, right? Because we can generate the direction of our magnetic field using a right-hand rule if we know the direction of our current, and if we choose the same direction to be in the direction as of the integral that we're doing, then the right-hand rule is going to suggest a positive direction for us all the time, right? So I think it's fairly easy to see how this is going to end up just being the negative of this. But what if we do something a little more complicated, and we don't actually do this in a circle? We kind of use two circular regions, but chop off just a quarter of each. Okay, so this is a little more complicated, but we're going to see that this is actually going to add up to give us 0. So you can see it here. This is going to give us 0. Now why does this give us 0? Okay, I kind of talk about it in this bottom paragraph here. So what's happening here? Let's start off and let's take a look at the contributions from each of these four sort of sections separately, right? We have them labeled here. These corners are A, B, C, and D. So we can talk about things like the straight line DA and the straight line segment BC, and then we can talk about the curved segments CD and AB, right? So let's start off by looking at the straight line segments DA and BC. Okay, so DA and BC. In those regions, we know that our magnetic field lines everywhere are circles around our conductor, right? And they're going to be directed in this direction because our magnetic field, again, follows this sort of right-hand rule. But because we're running radially in both of these sections, our DL, our tiny little length segments, are everywhere along these segments, are everywhere perpendicular to B, right? So B is always perpendicular DL on the line segment DA and on the line segment BC. Because of that, our B dot dl just goes to 0. So this section and this section contribute nothing. They're just going to add up to 0. Now, as we go along the curved sections, let's say we take a look at AB first, this outer section here. Okay, so AB, we're going in the direction of our magnetic field, right? Again, following the right-hand rule. So just using the logic that we talked about above, if we're going in the same direction, we're going to pick up a positive contribution, right? And when we're down here on the segment CD, we are going to pick up a negative contribution, right? And now AB is longer than CD, so we might think, well, we're going to get more length as we go along here, but it's also true that we're farther away from the conductor at that point, and so while the line that we're integrating over is longer, each infinitesimal segment picks up a smaller contribution from B. And so it happens, and you can do this, you can actually do the calculation, but I'm just going to mention sort of how it works. You're going to end up seeing that because we're closer here along CD than we are on AB, and the magnetic field scales as 1 over r, but so does the length of the circumference of a circle. It scales with r. These two things are going to cancel out exactly, because in here we have a minus sign, right? We're going in the opposite direction of the magnetic field, and here we're going with the magnetic field. So this positive contribution cancels exactly with this negative contribution, and we end up finding that this closed integral, this closed loop integral around this loop ABCD gives us 0, okay? And this is kind of leading us one step closer to the sort of full application of Ampere's law. What have we learned sort of so far? Well, we've learned that if our closed path encloses a current, then it's equal. Then our integral around the closed loop is going to be equal to mu naught I, right? Or maybe negative mu naught I, depending on the direction that we choose. But in any case, if we're enclosing some current, we have this value. If we enclose no current, then I is 0 in a sense, and our closed loop integral here gives us 0. Okay, so if we're enclosing current, we have some non-zero value for that loop integral. If we're enclosing no current, it comes back as 0. And really, I mean, we don't have to remember them as two separate facts, because when you think about it like this, and you think about this I as not just some current, but some enclosed current, then here we're enclosing current, and these are non-zero. Here we're enclosing no current, and it's 0, right? And that's the way we're going to write down Ampere's law here in a second. Okay, so we did all this for a very sort of specific shape of path integral here, of our line integral, right? We're picking only circles, right? And then we picked here, I guess in this case we picked sort of two quarter circles, and then two lines that were very clearly going to give us 0 because they're perpendicular, or at least the line segments are going to be perpendicular to the magnetic field. But what if we wanted to do this integral around some kind of weirder shapes? Let's say we were looking at shapes like this, right? We're going to see that the same idea is going to hold in this case, okay? We're going to see that if we integrate along these paths, so let's say we take a look at diagram A here, okay? What is our B dot dl? Okay, if we look at the diagram, the angle between B and dl is always going to be phi here. You can see it here. It's going to be the same idea over here, okay? So our B dot dl is always going to be B dl cos theta, okay? And then if we look at the diagram, again, look at diagram A here, we're going to see that our dl cos theta, which is just this little part here, right? Because we're basically projecting dl onto B, so just this very small part here is going to correspond to the length of dl cos theta. Well, that's exactly the length of r d theta, right? And why is that? Well, that's because this tiny little section of arc is our d theta, and it's going to be scaled by r as we go further and further out, right? So so we find that dl cos theta gives us exactly, or dl cos phi, I should say, gives us exactly r theta. And so we can write this closed loop integral here, b dot dl, as, and I guess I skip a step here, but we can see that we can write it as b dl cos theta, right? So this can be written as the closed loop integral b dl cos theta. Again, our b takes on this value here, right? Because we're still dealing with a long straight wire at this point, okay? And our cos phi ends up giving us r cos theta, okay? And so we end up with this setup here. Well, now we can just factor everything out that's not getting hit by the integral. We're only integrating over theta now. Theta is the only thing that's changing in time here. And so we need to do this integral of just d theta, this closed loop integral of d theta. But we're integrating d theta over a full circle, right? We're doing this integral of d theta all the way around the loop. So what do you get if you integrate d theta all the way around a full 2 pi? Well, you're going to get 2 pi, right? So this is just this 2 pi here, okay? And again, we can see that this is going to cancel with this, and we get the same result in this case. So we end up with this closed loop integral, and b dot dl gives us mu naught I again. And this is true as it was true back for our circular paths. This is true for any weird shaped path that we may choose. These kidney shaped, potato shaped things, still true. Okay, no matter how we do it, it's still going to be true. Okay, so I'll leave those notes there. And now maybe the last thing that we want to note is that, let's say we started piling these together, right? Let's say we had multiple wires with multiple currents. We could just do the integral over and over for each one of those separate wires and add the whole thing up. In this way, this principle of superposition that I've talked about a couple of times in the course lets us add up all these contributions from each of the wires, and it builds up one result that's going to give us the magnetic field for the sum of all the currents that are being enclosed by our loop. And maybe I should note here that we end up with the same result here. So it's kind of hard to see over here, but here we're enclosing current, right? So this is going to be this loop integral here is going to give us a non-zero value. Here we're not enclosing current, and the way this works is we're going to be picking up positive contribution from this chunk that we're integrating over here, but at the same time we're picking up some smaller in length, but equal in magnitude, because b is stronger over here, contribution over here. So as we do this full integral, we're picking up contributions from like here to here. The rest is going to give us 0 as we go around the rest of the circle. But the whole way in here, we're picking up negative and positive contributions, and again, this ends up giving us 0, right? And that's what we would expect, because we're enclosing no current, right? And so as I was saying, let's say we wanted to do several currents. Let's say I had another current running in this direction and one running like this or whatever, and we wanted to get the integral around this closed loop for all these currents. Well, we would just do each of them on their own, add them up, and it would give us the answer that we would expect to get. So there is a principle of superposition at work here. We can add up all of these contributions, and when we do that, when we sort of phrase it in those terms, it really gives us what we call Ampere's law. Okay, and here is Ampere's law. Maybe I'll try and get that on screen. Okay, so Ampere's law tells us that the line integral around the closed path, so whatever closed path we're choosing, is going to be equal to this dot product, b dot dl, okay? Or no, I think I misworded that, I'm sorry. So the line integral around a closed path of b dot dl, this dot product that we see here, is going to be equal to our mu naught times the current enclosed. Okay, so we can kind of see it at play in this diagram down below here. We have multiple currents running through here, right? We use our right hand rule, so we're gonna use our right hand rule to have our fingers curl in the direction of the the direction of the loop that we want to be integrating over, right? So our fingers are going to curl. We can see that our fingers are going to curl like around the loop like this here, right? And then our thumb is going to point in the direction of what we're going to call positive current flow, okay? So in this case, I1 and I3 will pick up positive signs, and I2 will pick up a negative sign. And we can kind of see that here. They kind of draw it in a top-down view. Our right-hand rule, again, gives us this direction for positive, right? Or this is the direction our fingers curl in, so our thumb tells us that upward is positive. So I1 and I3 are positive, and I2 comes in with a minus sign, right? And so using this Ampere's law, we can often, if there's sufficient symmetry, we can often get at B much more easily. The same way we kind of use Gauss's law to look at enclosed charge and get E from where we can pull out E from that integral. Same thing is going to happen here. We're going to look at enclosed current. Where there is enclosed current, we know that this line integral is non-zero, and then it becomes a question: is there sufficient symmetry that we can actually pull out B from that integral easily, right? And so we're going to take a look at a number of examples of that in the next video. But for now, I'll leave it here, and like I said, we'll look at those examples in the next one.